This is a video that I'm making to explain a little trick that I used in class, or maybe a little shortcut that wasn't explained. So in class, I've been solving, or it's often convenient to solve, equations that are basically non-dimensional in form. So like look at the lower equation here. So in class, I might have solved something that looked like du dt equal, du squared dx squared minus u, which kind of looks like a fin equation, but not exactly. It doesn't have any of the, the materials properties or dimensions in it, really. And the question is, how is that connected to the real physics, right? So like for real fin, you have that the rate of change of storage per unit length, or per cross-sectional piece is c times the cross-section, or so the heat capacity times the cross-sectional area of the fin times d temperature d time equal a portion that has the diffusion component minus a portion due to heat loss through the boundaries via convection. And that of course comes with a constant h times p for a fin, where p is the perimeter, the outer perimeter of the fin. So the question is, how do we go from that to this non-dimensional equation that is actually a lot easier to solve? All right, let me just pull this equation back over to a blank page and show you how you go from a real physical equation to a simple non-dimensional one. So let's start by just cutting and pasting the equation that we actually want to solve. And then the trick is basically to make a change of variable. What we're going to do is we're going to change the definition of time and the definition of x so that the little prefactors that appear in front of them go away. So we're going to make a change of variable. So what do I mean by that? I mean that I'm going to define x, like the independent variable x, as some constant times a non-dimensional version of x. So I'm basically going to swap out what the independent variables are. So x was a dimensional number. X star is going to be a dimensionless number. And the thing that connects them is some characteristic length scale that I'll call x sub c. And I'll choose the definition of x sub c such that it makes the equation simpler. So if you're not quite sure what that means, just stick with me here. I'm going to do the same thing. So I'm going to do the same thing for time. So I'm going to redefine time in terms of a characteristic time scale times a non-dimensional version of time, or a dimensionless version of time. And then what's left to do is figure out how I should define these characteristic length and time scales such that it simplifies the governing equation. So let me show you how to do that next. So then what you do is you take the definitions of our transform variable and just plug them in. They only appear inside the derivative, so it's not that hard to do. And then the thing is that, the constant that sits inside the differential can just come outside, right? It's just a constant. So the first term will pop out a term that looks like 1 over the characteristic time scale, and the second one will pop out a term that looks like 1 over the characteristic length scale squared. I'll show you why the squared comes up in a second. And the last one doesn't have any transform variable. If I'm unsure why the xc squared comes out, then it's probably easiest to think about this as separating the partial derivatives and doing them twice. So each time you have a partial derivative with respect to x, it's going to pop out a factor of 1 over xc, and then that operation happens twice. What I'm going to do from there is actually divide through by c times a over tc in order to group all the prefactors into some simple looking things. All right, so by doing that, I basically get rid of the prefactor for the first term, and then I get some prefactor for the second term that involves diffusion and a different prefactor for the third term that involves the convection. But then the key thing is to basically look at what these prefactors are. And in this case, we actually get to choose what the definition of the characteristic length and time scales are. And I'm going to choose them based on the values of things that exist in the problem, like h, p, c, a, k, blah, blah, blah. So how do I decide how to define them, or what is even a valid choice? Well, I just look at the prefactors. I would like those prefactors to be as simple as possible, and so in fact I'm going to just choose them by definition to equal 1. And that actually tells you what the definitions of the characteristic time and length scale are. The second prefactor is the only one that contains the characteristic time scale, and so that tells us to make that prefactor equal to 1, I would have to define the characteristic time scale as c times the cross-section divided by heat, the heat transfer coefficient times the perimeter. And then if I look at the first term, it involves xc squared. So in order to make the first prefactor 1, I would have to set xc squared equal to k over c times the characteristic time scale, which we know from the above box. And that tells us that the characteristic time scale is square root of k times a over h times p. All right, so with those definitions of the characteristic time and length scale in hand, then we can sort of finish it off. So if we make those substitutions, then basically it gets rid of all the prefactors that were showing up there. And basically you get a new, not quite dimensionless equation, but something that's quite close that doesn't have any prefactors. At that point, you might declare yourself done, but if you want to, you can actually go a little bit further. You can non-dimensionalize that equation. So the equation is not actually dimensionless because temperature is still up there. So that the equation has dimensions of temperature. You can non-dimensionalize. Actually, usually in this case, you wouldn't necessarily non-dimensionalize. You would define something like theta, which would be t minus t infinity, which really only gets rid of the t minus t infinity that appears in the back half of the problem, or the last term. So that'll actually make it look like what we wanted, but it's not technically non-dimensional. A lot of times it is actually a good idea to non-dimensionalize because you also have to worry about what the boundary conditions you're going to plug in are. So if you want to non-dimensionalize, what you can do is define, t minus t infinity, but then divide by something else that has units of temperature. So usually this would be like an initial condition minus t infinity, or it could be some characteristic temperature that exists in the problem. In that case, you recover exactly the same differential equation, but it does some nice things to the boundary conditions if you set it up right. So, for example, if your problem specifies a fixed base temperature that takes over at time equal, at the base, right? So at x equals 0, maybe you have a constant base temperature, then you would define the t minus t infinity part as the base minus t infinity. So if you do that, then at x equals 0, you'd come away with the fact that u is in fact equal to 1, which is a nice boundary condition to work with. If you have the more complicated condition where the boundary condition is, let's say, a fixed heat flux at the base, you can actually still non-dimensionalize to make that look easy. It's a little bit trickier, but the same idea basically holds, is to choose a characteristic temperature for the non-dimensionalization that makes the boundary conditions look simple. So in this case, it's a little hard to figure out what that is. So what you should do is just plug in the definition of the characteristic length scale and the characteristic temperature scale that you're looking for, and look for something that would make that look simple. So in this case, there's a back half term that looks like du dx star evaluated at x star equals 0, but then there's a prefactor, right? So the objective is to make that prefactor go away and give you something that looks like du dx star equal 1. And that happens if you choose the difference between, tc and t infinity to be equal to, let's see, in this case, that would be kac over xc over qb. So you have to reach back and look up the definition of our characteristic length scale. I think it was square root of Ka over HP. And so if you plug that in, you'll get square root of Ka times HP divided by the base, the heat at the base. And making that substitution for t minus t infinity makes the boundary condition be, du dx equal 1, which is easy to work with. So then in summary, by making this change of variable, or making a series of change in variables for the length scale, time scale, and possibly temperature scale of the problem, you can convert dimensional problems into non-dimensional problems that are far simpler mathematically to solve. That's the basic idea.